Hello everybody and welcome to CS202 Online, Day 6. Sorry for the brief delay there when we were starting the stream. Now I'm here. So, by the way, the name of the theme song from the countdown is there's Valorant, Overwatch, Fortnite. So there's a mixture of those themes. So everybody good? Everybody's here? Did you all leave? You thought I died? Left the chat? I don't know. I was gonna start the stream, but then I forgot I had to do something, so I went to do it and came back. That was a delay. But anyways, so feel a little better now this time. So let's give this pointer thing another try. So we're gonna kind of briefly go over what we did last time and then continue. That way, in the case that we missed anything last time, then we'll get it this time. So, sounds good, everybody here? Like I said, there's no response. I don't know. I think we're online. I hope we're online. Okay, it's good. Yeah, sounds good. Cool. All right, so there's a response. Cool. All right, so let's go ahead and start by talking about the idea of pointers again. So we have variables that can keep data, and that data that we keep are integers, floats, doubles, custom data types, strings, all of these things. And amongst this data, one of the things that we want to keep are addresses too. And addresses are going to be the location of those variables and where they reside. And so pointer variables is just that. It's another variable, it's another type of variable, it's a built-in type of variable, and it can keep addresses. So pointer variables can keep addresses, and these addresses are in hexadecimal code. And hexadecimal code starts with 0x, and the difference between hexadecimal and decimal is that hexadecimal goes from 0 to 15, but we use 0 to 9, and then we use letters A, B, C, D, E, and F. So, for example, 10 in decimal would become A in hexadecimal. 11 would become B, and 16 would become actually just 1 0. So yeah. Okay. So these addresses kept in hexadecimal code can be useful to reference a variable or to alias it under different conditions. So if I go ahead and create a variable b like this, I can create a pointer using what is known as the dereference operator. So the asterisk there is known as a dereference operator, and it is a unary operator. Okay. And so we got integer pointer, and this is just like any other kind of variable, except while this one is an integer variable, this one is an integer pointer. If it makes you feel better, one of the ways that you can declare it is you can put the asterisk next to the int and then do the variable name. And that way you can see that this is the kind of variable it is. So if we wanted to make a float pointer, we would say float star. PT, I guess, so that there's no naming problems. Okay, so while this is the dereference operator, when we are declaring a pointer, we also use the asterisk. So that's kind of the third usage of it. So we have the ability to do dereferencing with it. We have multiplication as well when you have it as a binary operator, and when you're putting it in a variable declaration, it's a symbol to signify that it's a pointer. And all pointers need to have a type of what they are. This is a little bit different than the C language, if you're familiar with that. In the C language, we have something known as a void pointer, which can kind of cover all and point to just about anything. And you would do that by doing something like that. And then you could make this point to an integer, a float, a double, doesn't matter. It would let you point to basically whatever you wanted. In C++, they kind of got rid of that, and to the point that I'm not even sure that you can compile a program with a void pointer. And even if you can, it's a bad practice because you typically want to know what you're pointing to, because that's the only sign that you know how to interpret the data. Because again, these pointers are pointing to addresses, but those addresses are locations of other variables. And those other variables in C++, they have to have a type. They could be an integer, they could be a float, and so on. So if in memory I have an address like address 100, and then I have here address 200, and in 200 I have a pointer that stores the address of variable 100, this is just a bunch of zeros and ones. So I need to know how to interpret those to know if the data is valid or not. It could be an integer, but it could also be a string, or it could even be a car. Actually, string is kind of a bad example because that would be potentially bigger, But a float, think about a float versus an integer, These are both kept as binary, but internally they're kept very differently because of the way that floating point notation works. The first bit is a signed bit, then you have, I think, the mantis, which I think is about 8, and then the remaining bits are for the actual value that you have, and I think it's stored actually as a fraction. And so it becomes quite a bit of a complicated mess that they'll talk about when you get to 218 or maybe 219. And so ultimately, you need to know what you're pointing to, because then if you try to dereference what you're pointing to using the dereference operator, so if this pointer, I'm giving it a nickname and say this is called v, variable v, and this is pointer pt, if I'm dereferencing pt and I'm telling the computer to print it out like this, it needs to know what it's printing, and so because that way it can interpret it and print it correctly. It's like if I tried to take a car and cast it as an integer before printing it, I'd get a number, right? What number would I get? Whatever the car equivalent of that is, but that might be a meaningless number, or vice versa. If I have an integer and I try to cast it as a car, two things can happen. One of them, I'm going to get some random car if it's a small number, but if it's a big number, it's going to overflow. I'm going to get an invalid character printed out, so I kind of get something like a little question mark printed out, right? So essentially, that's why pointer variables need a type, because they need to know what they are and what you're pointing to, so that when you dereference it, you can work with it. You can print things out, you can store things, and so on. So those are pointer variables. And then how do you actually access the address of a variable, whether it's a pointer or a regular variable? They all have to be stored somewhere. And in your memory, you have something known as stack and heap, and they're all stored in RAM per se, in your RAM stick, in your main memory. And ultimately, the stack and the heap grow from their own, either bottom or top, into the center. And the reason that you have this configuration is because when you have, we will talk about stacks at the end of the semester, but ultimately they grow by just feeding things on the top, so like feeding things in the top here. So it's like a stack. You're literally building a stack of something, right? And so it fills up this way. And so if you have a stack sideways, like lying down on the ground, and you have somebody here filling things up, and you have somebody here filling things up, you start filling them this way. They grow this way. The people here grow this way, and eventually they're both going to meet somewhere, right? Well, memory, you can think of it this way. When you're allocating things in memory in the stack, it's growing this way, and when you're allocating something what's known as the heap, it's growing this way. However, by having the flexibility of them growing from different sides, if a program uses a little bit of stack but not so much heap, it's maybe this is as much a stack as it uses. But on the heap, it uses a lot of heap operations, a lot of data in the heap. It can grow and use this much. And as long as they don't touch each other and they don't overwrite each other, because eventually you're going to try to both write in the same spot, then this is okay. But this gives you the flexibility that you can have another kind of program, a program that uses a lot of stack space and very little heap space. So in this program, let's just imagine that this is a 8 gigabyte memory, okay? This is about 7 gigabytes here, and this is about 1 gigabyte. And then over here we have maybe 60 gigabytes and maybe 2 gigabytes, okay? And the entire memory is 8 gigabytes big. If I had, one of the ways that I could implement this, I could say I could buy 2 sticks of RAM. Each one is 4 gigabytes. And I can say this one is my stack, and this one is dedicated to my heap. And in that situation, I have 8 gigabytes total, but I can at most use 4 gigabytes for one of the categories. So if I have this program right here, you know, I can't fit it in memory. I can't fit it because that 6 gigabyte is too big for my 4 gigabyte stick of RAM. So by having the flexibility of being able to have it all shared between one big stick and having one grow and the other one shrink and vice versa, I can, in an 8 gigabyte stack, I could fit this program and this program. Whereas if I had them separated by having each one have allocated unique areas, then these programs would not fit. Obviously, if I had a program that just required 1 gigabyte of heap and one of heap, you know, then yes, this would work here fine because they would just fill up 1/4 of each of these. But then again, you know, I'm trying to maximize my resources, and that's the idea behind using a stack and a heap, that they can grow dynamically. So programs that are very intensive with one side, then use that and still have the ability to have also a stack in there or a heap in there, you know, both. Now, of course, if I have a program that uses 3 gigabytes of stack and 60 gigabytes of heap, now that's when I kind of run into a problem. So like if I have, you know, a program, typically what's going to happen is when you create a program, it allocates space on the stack. That's all your variables that you declare when you're running your program. Those regular variables that we've been using so far in 135 and 202, so you can think of them as like static. It means that they're always going to be the same variables that you need every time you run the program. You're always going to need them because you use them in the program. So let's say that those variables happens to be 3 gigabytes of data. So that fills up this much, okay? And so from there, you're going to then dynamically, because we're going to learn about dynamic allocation, dynamically allocate stuff. So let's say you're using a vector, because vectors are dynamically allocated. And those vectors, you know, you start inserting things into the vectors. And it turns out that you are slow, you know, right now you're at 5 gigabytes, but then you're going up and you have to fill it with 6 gigabytes of data. But bam, here you go into a problem. Here, because you only have 8 gigs, and you're using 6 of these and 3 of these, that's a total of 9, which means that now you're doing what is known as stack smashing, I believe. And if not, then what is definitely known as Stack Overflow, which is where the name of the popular website comes from. So I'm not sure if the stack smashing is that, but definitely Stack Overflow is that problem. So that's where the people at Stack Overflow came up with their name. That is that means that you're overwriting stuff that you shouldn't because you ran out of space. Now, what happens in your program? If this actually happens, your program crashes. Okay. So what does this mean? We need more memory, so we can insert another stick of 8 gigabytes of RAM. Now, that doesn't mean that we're going to make the stack be 8 and the heap be 8. We still are going to have 16 gigs of RAM, but, you know, we may start filling out the stack from here and the heap from here. And then potentially, you know, the stack could go all the way here, and then the heap use like this much. Or, you know, you could have the heap use this much, and then the stack uses this much. Now, don't ask me on average how much each program uses, but I would say if you're doing that, obviously, if you're doing that things dynamically, as you probably should, then there's going to be more heap usage than stack usage. But we will revisit the concept of a stack in general at the end of the semester, so 2 weeks from now, I guess. And then you will learn more about memory management in later classes since you're a CS student. So, but that just kind of, the whole reason that I'm going into this is because, as you saw last time, but then I'll show you again today, when you're looking at the address of variables, the address of the stack is very different than the address of the heap because you're starting from the end and the beginning. So the address is really big when you're looking at the stack, and it's really small when you're looking at the heap because they're building up like that. And you could actually, if you don't do this because you probably crash Sally, but if you were just allocating memory and looking at the address of that memory and seeing it grow, eventually you're going to see how they get close enough, and the moment they're about to overlap, that's when your program's going to crash. Now, in reality, there's other checks, like I think they added, they're only going to let you allocate so much memory before the program itself, yeah, you're allocating too much and crashes you. So there's other checks to avoid this stack overflow that just kind of hits, you know, that's kind of like the worst case scenario. You're more like running out of your own little stack area that you have. So there's checks to avoid this kind of thing, so you don't just casually do it. Just like there's checks to prevent you from accessing variables that are not yours. So how do you, if you were to access the address of another variable, you could also potentially store in a pointer variable any address that you wanted. Like I could store address, a hard-coded address, and I'm not gonna do what I did last time experimenting with that stuff, but what you should know is that you should never assign an address directly to a variable. In fact, this will not even compile. If you want to compile, you have to use a special flag called fpermissive, which is kind of like the YOLO flag in the sense that it lets you do things that you really shouldn't be doing. And it's just like, well, I guess if you really want to do it, go for it. But the flag is kind of like permissive, meaning like it's giving you permissions that it really shouldn't. It's trusting you not to do something really bad. 99% of the time, you're probably doing something really bad. So that's why last time we were playing around with that. So don't ever try to manually assign stuff to a pointer. What you will usually do is you will assign the address of a variable that you currently have. And for that, you're going to use the ampersand operator, which is known as the address of operator. Okay, and that operator is going to return to you the address of whatever you're calling it on. So if you have an integer b, whether you initialize it or not, when you declare it, that is putting in, well, technically, I guess you have to initialize it. If you never use it, it seems like the compiler will ignore it because it's smart enough to see that you're not using it. So that's what happened last time when we were messing around. But if you if you declare a variable and you assign something to it, and now it has to be stored in memory somewhere, and you want to get the address of that variable, you can, if you want to just print it out, you can say cout address of b, and that's going to get you the address of variable b. And so that is going to be a stack variable, so it's going to be one of those big addresses that we see. And that is more of what you would want to use the address of operator for. So if you want to make a pointer, so let's say make p as a pointer, what we can do is we can say p is going to store the address of b, which means that now in memory, both p and b are both stored on the stack. So they're probably close to each other, actually. And it turns out that when you do this, this is going to take this address where, let's say that b is stored, p has a 5 in there, and it's going to put it here. So it's going to put address 100, okay? And that's more of the manipulation that you want to do. So now you can think of both p and b pointing to the same location in memory where you actually have the b stored. I could create more of that. I could make another pointer called t, and then do the same thing. T gets b. And so now I have p, I have t, and they're both pointing to basically a b, which is in the stack. And if I change with any of them, so if I dereference t and assign 6 to it, it's going to change b. It's going to change the location of b, or not the location, the value of b, and change it to 6. And then if I try to cout t, b, p, which one's the pointer, p or b? P. Or b, any of these will all give me the new value of 6. So messing around with pointers can be risky because you may accidentally change things that you don't realize you changed. They're all containing the same location in memory at this point, which means a change to one of them will do a change to all of them. And so yes, that's called aliasing, and it's a powerful ability, but dangerous as well. Now, why talk about pointers in general? Why ever use them if you can just go access stuff directly with B? Well, the reason why is for dynamic variables and dynamic memory allocation. With dynamic memory allocation, we want to create variables at runtime. Okay, so right now all the variables that we're using, they're technically created at compile time, which means that there's a fixed size of how much data your program can take. And very few times is that a reality. Most of the times, we don't know at compile time how much data we're going to be dealing with. If we're processing a file, we don't know the size of the file. Now, we could try and estimate what the biggest a file is and then always just allocate that much memory, but that's wasteful because if we don't use that much memory, then we are wasting space in the computer. And vice versa, if if we just have no idea, like how much space we're using, and sometimes we might use just one integer, or maybe we'll use 10,000 integers, and maybe we'll use 1,000,000 integers. If we have just no idea, then we can't declare something and then run out of space and then crash. So with dynamic memory allocation, at the time that we know, which is when you're running the program, how much space of data we need, that's when we can at that time ask the operating system, like, hey, can I get some space so I can store this data? And the operating system has the heap, which is exactly what that is for. It is for where at runtime you wish to use space. And so whereas your normal variables are in the stack because it's always fixed the same size, the heap is basically like free space for rental that you can take, use, and then give back. And so the way that you take space and you ask for space for the operating system is with an operator called new. What the new operator does is it requests the operating system space. Now, how much space? Well, you have to give it a data type. You have to tell the operating system how much space you want. And space is going to be related to the data type. Why? Because some data types require more or less space than other ones potentially. So for example, an integer requires, depending on the architecture, may require 4 bytes or 8 bytes depending on what computer you're running. So for now, we're going to stick with the 4 byte because that's pretty normal situation. However, if you're requesting a double, that more than likely requires 8 bytes. That's usually twice what the integer requires. However, you're not limited to built-in data types. You could also create a class object using this system. So if you have a class A, and in this class you have an integer x, doesn't matter if it's public or private, then you have an integer y, and maybe you have a double g, okay? And then if you go ahead and allocate an A object, so you would do new A, this will allocate how much space you need for that object. Now, how much do you need? Well, you can do the math in here. This is going to suppose that an integer requires 4 bytes and a double 8 as we set up here. In this case, this requires 4 here, 4 here, and 8 here. So you basically add them all together and you get 16. It feels good when you can actually do math in your head. Yesterday I could not do math. So yeah, 16, okay? So that 16 is how many bytes you need. So the operating system needs to know that number to be able to actually give you that much space. And so the new operator requires you to put the data type that you're building in there, or the class if it's the class that you're making, okay? Which again is a custom data type in other firms. And so the syntax is again going to be new, and then the data type, and then the semicolon. Now you can also make an array of whatever you're doing, and for that you can say new data type, and then the number inside, which is called an integer expression, because technically it could be something like 2 plus 2, which again, you could just put 4 in there, but it could be variable. And that's the other big power of it. You don't want to hard code this because at that point, if you're hard coding an array that you dynamically allocate, then I question as to why you're using the array in the first place, dynamically allocated versus statically allocated. Although it might be because you only use it part of the time of the program. That could be a valid answer, actually. But more than likely, the kind of syntax you're going to have is you might have something like cin a. And integer a is something on the stack, yes. But that a you read in from the user as like the number of items you need to read into your program. Like if you're redoing assignment 1 using dynamic allocation, then instead of vectors, then you could actually go ahead and that's a good idea, because I was thinking of what assignment to give you guys for allocating dynamically, and I think I will do that. I think I'm gonna take assignment 1, and then I'll forbid you from using vectors, and then you're gonna have to create your own sort of vector class. Because I was thinking of doing that already, making you do a vector class, but then here now you get an application of it. So yeah, and it will kind of be a remake of when my AI took 202 when they were redoing their first assignment with dynamic allocation. So it would be a fair thing to do. So yes, you will redo the Twitter assignment with dynamic allocation. I'll go ahead and write up something to explain that later. But yes, that will be your weekend. That's the end of your weekend there. So anyways, yeah. So back to this, here then you can go ahead and put that A in here, And then now you can dynamically allocate an array of any size that you want based on what the user entered. And this is something that's decided at runtime. Now, I know what some of you might be saying who might have not taken me for 135. You know, you also say that I could do something like this: int a gets b. And you're like, I can achieve the same thing using that. Yes, you can. However, the way this is working is it's the compiler helping you out by saying, okay, this guy doesn't know what he's doing, so really this needs to be dynamically allocated. So you'd actually see, if you check this, that this is being stored on the heap, and it's actually doing dynamic allocation, but it's bad because at that point you can't never deallocate it, and really bad. So you never want to do this. When you're doing, you know, old school arrays, static arrays, you have to give it a size. You have to say int a and then give it a size. If you don't, then you're doing it wrong per se. If you have to be using dynamic allocation, that would be the correct thing to do. Everything else is the compiler lending you a hand because you're like not sure of what you're doing, and the compiler wants to let you compile and run programs, and it's just kind of like, yeah, we'll let it slide, but it's not the right thing, you know. And so you don't want that to happen because you want full control of what's happening. Because if you don't have full control, if you run into a bug, then good luck, because you know, it's like you let the compiler do so much that at this point the compiler is the one who wrote the program, and you know, good luck trying to fix a bug because you didn't write it, the compiler did at this point. So yeah, blame the compiler now for the bug, I guess. So yeah, so anyways, that's how you declare a variable. And now here's the thing: just doing this is declaring the variable, but you're not storing that address anywhere, because what new does is it allocates the memory from the OS and it returns to you that address location. And that address is just being thrown away at this point. So what we need to do is we need to store that address somewhere so that we can actually use the new variable that we just allocated. And that's when pointer variables are going to come to the rescue, because I can do something like in PTR, and that's a pointer variable. And now I can do PTR get new integer. And so this is what's going to happen now is I'm going to basically have and take, you know, I'm going to allocate an integer. The OS will allocate an integer at my request. And then this will return to me an address of that integer. So something like that. And I'm storing that in PTR. That way, now if I would like to actually, you know, store something in PTR, I can use the dereference operator and then assign, I don't know, 10. And then I can go ahead and print out 10. And there you go. Now we have full usage of this brand new created integer in the heap. And if we want to do this with an array, let's go ahead and do that. Same program, why not? Let's go ahead and say ptr get new int and then a number here. For now, we're going to put a fixed number, but again, if we want it to really do this useful, we probably want to read this in from somewhere, because that's why we're doing it dynamically. But we can also put a fixed number if we really want it. So bam, this creates an array. And so if by this creating an array, I can now access all of the elements. So if I wanted to access into index 0 per se, I could say something like ptr gets 8, and that's the same thing as saying ptr 0 gets 8. These two are the same. I can also do ptr plus 1 gets 10, and that's the same thing as doing ptr 1. So you might be asking yourself, what the heck is this? That is known as pointer arithmetics. Pointer arithmetics is basically playing around with addresses, and by adding to an address or removing to an address to be able to access neighboring addresses of what you're working with. So when you allocate an array, dynamic array, or even when you're working with a regular array, actually, it doesn't have to be dynamic. When you're working with any arrays, in main memory, it's going to give you a section of memory to store. So in this case, we have 5, right? We made it size of 5, I think, yeah. So it's going to give you 5 slots that are going to be next to each other, or at least to you, it'll look like that. When you get to 219, we might see if this might not be the case always, but forget about that. For now, naively think that it's giving you the memory as everything together, okay? So when it does that, when it gives you memory together, like this, then the 8 is being stored here, the 10 is being here, and then your other 3 variables or other 3 indexes of your array are basically being stored after that. So 0 to 4, okay? And so this is useful to the fact that everything is stored together, because if we're looking at the addresses, this could be address 100, this could be address 104, 108, 10C, and then 0110, okay? Yeah. So first of all, you might be like, why are we not going increasing of 101, 102, 103, 104? The reason for that is because how big is an integer? An integer is 4 bytes, and these are addresses in terms of bytes. And so when you talk in 219 about how things are stored, main memory, it handles what are known as words. And so words are going to be your unit of measurement, and your word is typically connected to the size of an integer. So if an integer is 4 bytes, then each of these is going to be a word. And they're, that's why in assembly, when you take assembly, they're going to talk about the word and those kind of terms, and that's where that's going to come from. So that's in your future as well. But ultimately, for now, just know that each of these sort of sections of memory, it's split into 4 pieces, but you don't go one by one. You go in multiples of 4. So it's like if you're buying a plot of land, and they don't just sell you land by 1 meter square. The smallest lot you can buy is 4 meters squared. And so you can buy 4 meter squares, or you can get an array that's like, size of 5, which means 20 meters squared. And they're all 4 meter square pieces that are going to be, next to each other. So I know meter square. Let's just think about thousands of square feet. They only sell you in blocks of 4,000 square feet. Which one? I don't know which one the right word is for that. Square feet. Square foot. I don't know whatever foot or feet. Which one is for multiple number of feet. So I guess foot. No, it's feet. I don't know. English is weird. So, anyways, yeah. So ultimately, when I'm doing the pointer arithmetic here, even though I am adding 1 feet, so it's feet. So you would say square feet. Okay. So then, all right. So then basically we have 4,000 square feet, and that's the smallest amount of land that they'll sell you. Even though the lots themselves are, they're going by 1,000 square feet. With 1,000 you say square foot though, right? 1,000 square foot. They only will sell it to you in increments of 4, and so you can buy 4,000 square feet, or you can buy nothing. Even though the land cost is going by 1,000, they don't sell you 1,000 bits. They'll give you 4,000. So you can buy 4, you can buy 8, you can buy 12. Or in our case, we're buying 20 because we're buying 5 slots. Okay. Of course, here the OS is free. This is like communist memory, free memory for everybody. You just have to request it. So yes. Okay. So yeah. The other thing is when you do the pointer arithmetics here, you're saying +1. This +1 is not just increasing it by 1,000 square feet, or in this case by 1 byte. No, it's increasing it by the size of the type of the pointer. So because this is an integer pointer, that means that when you're saying an integer pointer +1, what we're really saying is you have to increase it by the same size of this. So because this is 4 bytes, when you say +1, we're taking the current address, so maybe this one, +1, that's actually going to be +4 bytes. So that's why you get 104. And the reason that you want to do this is because it makes the math a lot easier, actually. Because then you can quickly go down between indices of the array by just saying +1, +2, +3, and +4. So chat, what if I had 0x +3? So if I had PTR +3, what address would that be? So looking at this, the answer is on the screen, but you guys tell me, what would be the address of doing 100 +3? While you guys answer that, I'll take some water. No. I'm like, what is the answer? And look there, I see the word feet, and I'm like, no, that's not the answer. That's what they answered earlier. Do we have to encompass in parentheses PTR4, or is that just for readability? No, you do. You do want to encompass it, because if you don't, it's going to dereference it. So I wasn't getting into the official syntax, but yes, when you're doing this pointer arithmetic stuff, you actually have to you got to make sure you do this, because if you don't, there's order of precedence with operators, right? Think about like when you're doing 2 plus 2 times 3, right? In this case, you multiply first before you add because that's the order of operations. So what happens with the dereference operator here is that if you just do PTR plus 3, this is going to dereference PTR. So it's actually going to give you the location of PTR, which is like 10 or whatever that has in there. So whatever is here, 8. And then you're actually just adding to the value of PTR. So what you're really trying to do is you're trying to add to the address. And so what you need to do for that is you need to actually make sure that the addition happens before the dereferencing. So yes, you would need to add parentheses. I didn't want to get to that because I don't want to confuse you, but I guess now we crossed that bridge at this point. So anyways, now that you've seen that, what would be the answer to this though? So the parentheses in this case are quite important actually. So what would be PTR plus 3? What is the answer to that addition? What address are we going to get back? No, I'm glad you asked that because like I said, that's something that means that you actually you're catching on to this pointer arithmetic stuff. So 10C, very good, very good. You guys got it right. So it would be indeed 10C because it goes by increments of 4. Now they gave me another one. Let's say we got a double pointer. Because we'll call this one DTR. If you got this pointer, you know, and let's say that is address F100. Okay? And then I go ahead and I do plus 2. So that would be the same thing as doing DTR plus 2. Okay? What address is that? What is this address going to be now? So basically, what is the result of this? Give you a hint. There's four things in there. So we got somebody that says F104. So that's one suggestion somebody gave, that F100 plus 2 is going to give me that. Does anybody else have any other suggestions as to what the answer could be? You can even run a how about this? Let's run a Twitch poll. So 0x. So save your answers. Don't write any other answers. So let's do a vote. We'll see what you guys vote. So okay. So 0x F100 plus 2. What is? And I'm gonna put a couple of different values here. First of all, the first one I'm gonna put is the one that you suggested. So 0x F104. Then I'm gonna put a couple other ones. Okay. Allow additional bytes but given bits. That's creepy. Okay. 2 minutes. That should be more than enough. So there's a question for you guys, and go vote. Democracy. Although this isn't really democracy because there's a right answer and there's a wrong answer. So yes. We got a very, very split decision here, by the way. This is quite interesting. Although we only have 4 votes, which is kind of worrisome because look, the votes are anonymous, guys. I can't see what you vote. I just want you to vote. I promise I can't see what you're voting. So just vote. Don't be afraid to vote. We got 21 viewers. I'm hoping for like at least 18 votes. You know, we won't have like 3 AFKers who might be like in the toilet or something. But the rest of you should be here. So vote. So we got 3, 1, 2, 1. So we got 4, 6, 7 votes. The rest of you are probably just AFKing, mining extra credit points, which is kind of sad. So we got 5, 7, 8 votes total. I have no, interestingly enough, I have no votes for the first suggestion, but I'm assuming that you're just not voting, or maybe you changed your mind. That's possible too. But yeah, okay, we got one more vote now. Now we got 9 votes total. And I'm just gonna actually pop it up for the last few seconds of the vote so you guys can see where we stand on the election here. This is 2020 election, right? And then you can't see the numbers, but you can see them here. I think you can see them right there, right? Yeah, you can see the numbers there. So, oh, last second. It looks like last second somebody won. I think if I shrink this, we better see it better. All right, so that's better. So we had a total of 5, 7, and 11 votes. So we had 11 votes final. And it seems that the winner of the vote is 0xF108. You know, it seems like the wrong person won this election, guys. I'm sorry. Fortunately, this is not the presidential election or anything like that. This is merely just a poll. And the answer of this is actually going to be, if this is a double, so it should be this one, the second option here. So that's actually the correct answer. So congratulations to the 3 of you, which again, I don't know who did what, but actually, what if I click vote breakdown? Does it tell me who voted for what? Let me see. That'd be great, because then that means I lied to you guys, but no, I can't see it. It doesn't tell me. See? It doesn't tell me who you voted, so I wasn't lying about that. It tells me just if you had voted with bits, I guess. Oh, you can also apparently use channel points to give extra votes. It's interesting. So anyways, so yeah, so technically you guys got it wrong. This was the right answer, and I'll tell you why in a second, okay? This would be the right answer if this was an integer variable. That would have been the right answer, but this was a double variable, and the double variable takes 8 bytes. And so because it takes 8 bytes and you have 2 of them, that means that you need to multiply it times 2. So basically 8 times 2 would be 16. And so basically, if you add 16 to this address, because it's hex, all that's going to happen is it's going to become a 1 here on this one right here, because it's going to go 1, 2, 3, 4, 5 all the way to F, and then it's going to become 1. So the answer is F110. So congratulations to the 3 of you that got it right. Shame on you for the rest of you. This could come up in the midterm exam in the future. So now you know what you got to practice. So yeah, that was good. I see who's awake and who's not. We even lost 2 viewers after that. Rage quit. So anyways, okay. So yeah, so basically what is happening here is again, this was the first suggestion, so we know that's wrong. So that's the right answer now. Okay, so make sure leave the right answer in the notes, otherwise people will be confused. So basically, pointer arithmetics, as you can see, can be a little bit tricky. And so because this is a double, and like we said that the double takes 8 bytes, if we wanted to, store another double in there, we have to do +1, and that would have given me 8 bytes later. So that would have been 108, because 100, 101, all the way to 107 are all used up by one double variable. And then 108 all the way to 10F are used by the second double variable, which means that the third double variable, which would be the 1 + 2, would be available at 110. And of course, add an F to all of this, because we had an F. I just threw the F just to freak you out a little bit, but whatever. So anyways, any questions about how I got the that value out of this? Are we good? Because like I can repeat it. I can repeat anything. And I want to make sure you guys understand how I got that 110 out of this. So anyways, I'll wait a few seconds to see if there's any questions. If not, we can come back to talking about our little array here. Obviously, pointer arithmetics, because it's a little bit confusing, you can see that the better solution to accessing stuff in an array dynamically is just to use the square brackets. And that just makes your life easy because you don't have to think about pointer arithmetics. When we talk about two-dimensional arrays or three-dimensional arrays, the pointer arithmetics gets a little bit more complicated than that, a little bit more painful. And frankly, you don't want to deal with that kind of just unfortunate math that happens there. So it's so much better, 10 times always better to use your square bracket. But sometimes situations arise when you have to use pointer arithmetics, and that's why you should be aware of them, especially if not you, but maybe somebody else uses them. And that way you don't panic if you see in the code a line like this line of code right here. You know, if you see this in the code, you're not like, what the heck is going on? What is this? What is he doing? This is a variable, and then he's adding, and then he's doing a little star there. Like, what is this? Now you know what this is, okay? So 2 doubles is adding 16 bytes to the address, right? Yep, because each double adds 8. So 2 of them is 8 times 2, which is 16. So because of hex, it becomes from 0, 0 to 1, 0. Because every increase of the second significant digit is basically an increase in 16. So yes, cool, cool, cool. All right. So again, you know, with practice, you'll get better at this stuff. Just like with math, you know, practice makes the master, or whatever the saying is. So okay. So back to our allocation of variables. You know, actually one of the things that I wanted to point out here is that there is potentially a bit of an issue here that I like to talk about. So let's kind of copy and paste this down here again, so that I low-key did this intentionally, actually, to bring up a point. Okay, so let's clean up this a little bit, just so that you can see it better. And then let me move this a little bit better. So there we go. And then we're going to put this here, and then we're going to add a semicolon so it compiles. And we are good to go. Okay, so this is the code that I had earlier. And as I said for review, this allocates an integer in the heap. And then, actually, no, not really. The next one does that actually. This does the allocation. The other one is this is just a variable in stack that happens to be a pointer variable, but it's just nothing, it's garbage. This one, however, allocates an integer in heap, and then I store 10 in that integer I made. Then I go ahead and print it out to test it. And then I'm so excited about this dynamic allocation that the next thing I do is I create an array. And I do. I create an array right here, right? So this line of code allocates an array. But now I have a question for you guys. What happened to this integer that has a 10 in it? Where's this at? Oh, that looks weird. Where's that integer at? I mean, it has an address, and the operating system gave it to us, was kind enough to give it to us. But we lost it. We lost the address. Because, like, we basically, yes, this is what is known as a memory leak. This line of code is creating a memory leak. And what a memory leak is basically let's do the example of renting from an apartment, okay? So you went ahead and you requested a single room apartment, and you got the address for it in a piece of paper, and you have it's like Memento, the movie Memento, where you forget everything from the day until when you go to sleep, okay? So to remember where you live, you have a little piece of paper that tells you everything you want to remember between every single day. And that paper has the address of your apartment, has the apartment number per se, okay? Cool. you were so excited that you wanted to expand because you got a little extra cash. You wanted to expand where you live. So you got a 5-room apartment now. Okay, so that was your array. But when you got it, you stored it in the same location that kept the address of your current apartment. So it means you overwrote it. So you took your piece of paper and you overwrote on top of your old apartment number, the new apartment number that has the bigger rooms. But you still have the other one rented out. But the problem is that when you overwrote it, now when you go to sleep and you wake up the next day with the memento thing and you forgot what you're doing, you don't even remember that you have a 1-room apartment that you also rented. All you know is that you have this current one. And because you don't know that you have it, you cannot ever return it. And if you don't return it, so you don't return your keys to your leaser, he thinks that you're still renting it and he's not going to take it back because you paid in advance for like eternity or something. Or again, it's free apartments, okay? So it's utopia, free living. The problem is you're not using it because you don't even remember where that's at. You know, and nobody else can use it. So now you got this empty apartment when there might be people like sleeping in the streets, you know? And so that is basically a memory leak. It's the idea that you've allocated dynamic memory. So you've allocated memory on the heap, but you've lost the address. And if you don't have the address, you can't deallocate it. So let's talk about deallocating. So before we talk about how we solve this memory leak, let's talk about deallocating. The idea of deallocating something is when you're finished using a variable that you dynamically allocated, you want to return it to the operating system so that other programs can use it. You know, because this is the operating system is giving you all this stuff for free, but there's a condition. When you're done using it, please return it. Now, there is one extra catch. When the program finishes, anything that you haven't returned will be automatically returned because they do keep record of what they gave you. But you can't ask it what they gave you. That's the other problem. You can't ask it like, hey, what did you give me? All they know is that when you die, they can pull up some super secure vault that tells them what you gave them. But it only can be done when you actually die, as in like when your program ends. So to deallocate memory, we're going to use the delete operator. Okay? And the delete operator is, the name might be a little bit misleading. You're not deleting anything because you're really just deallocating, which is you're returning the memory, okay? There's no deletion going on, so it's a little bit misleading about that. We will talk about the C version of these variables, which are malloc and free. I think free is a better choice of words because you're freeing something versus deleting it, you know? Better choice of words, so just bear with me with that. So how do you delete a variable? Very easy. Say you got let's do it in one line of code this time. Let's say we got ATR equals new int. That's how you dynamically allocate a variable and also declare a pointer all in one line. Okay, that's how you usually want to do it. So then, if I wish to delete this variable once I'm done using it, obviously there might be some code in between here where you're actually using it, otherwise why did you make it? Then all you gotta do is say delete and then the variable name. And then bam, it deallocates it. Now what does that actually mean? If I try to do cout ATR, and I'm dereferencing it, which means I'm trying to see out the contents of it, or even if I just do cout ATR like this. In either of these scenarios here, you will see that if I run this in here, in fact, here let me add some space here. So give me a second to move this. So maybe let's put this on the next page like this, and then let's go ahead and actually move this up. Oh, fail. Hold on. Right there, like that. Okay, so I got the cout of ATR, and I'm dereferencing ATR. So this one, the first one, the one that is in yellow or orange, whatever this color is, I think it's orange. That prints out the contents of what you store in there. Of course, we never actually stored in there, but if we go ahead and store something, you know, let's do ATR gets 5. then this would print out 5. Okay? The second line of code would actually print out the address of that we got from new integer. So if new integer happens to be stored at address 555, then this will actually get 0555 printed, okay? Then we call delete, which is deallocating it. But then we go ahead and see out them again. What do you think is going to happen here? What's going to happen here is going to be, we're still going to get 5 here, and we're still going to get 055. And what's even worse is if I go ahead in here and I say ATR gets 10, and then I call my cout statement again. So again, let me just copy and paste that. I lost it. There we go. All right, perfect. Then this will become 10 now because I modified it, but the address is still the same. So then you might be asking yourself, what is delete doing? If we didn't delete anything, well, yes, that's because delete doesn't really delete, it deallocates. Big difference. So what this is doing is like, when you delete a variable, you're telling the operating system, hey, thanks a lot for letting me borrow this. Take it back now, okay? And the operating system takes it back and puts it in its for a lease, available for rental kind of thing. So other people can grab it, but they may or may not grab it immediately. However, it's no longer yours. But because you still have the address, and because we live in the utopian society where we don't use locks, you can still walk in there and use it. So you can walk in there and actually still store data and still retrieve the last data that you had in there. Why? Because you still have the address written somewhere. Where do you have the address written? You have it in ATR. And because you still have the address, you still remember to go there and you can go. So ideally you're gonna be like, oh, I deleted it, I shouldn't go, because it's no longer mine. But then what happens one night? One night you're partying and you get drunk. And then you get drunk and you're going home, but because you're drunk, you forgot where you live. So you end up going to your old place, which is ATR's place. And then you walk in there, and you still have it. You go to sleep there, but guess what? Imagine that somebody else had already rented it. And then you get in there, and it's gonna be like that scene in Back to the Future when in the second movie when they travel back to the present, and there's like a family living there, and the guy comes out with like a shotgun. He's like, "Get out of here!" Bam, and he like shoots at him or something, right? That's basically what's gonna end up happening to you, because you're gonna run into problems with other programs who now lease that area, and even if they haven't, you're playing with fire because you're trying to use a variable that is no longer yours. At that point, you're I guess they call it like a squatter. You're in a place that doesn't belong to you anymore, and so it's a very, very dangerous thing. And the name that we give that in computer science, or at least in programming, is called a dangling pointer. So you've just created a dangling pointer. A dangling pointer is basically a pointer, and by the way, an ATR in this case would be that. So ATR would be a dangling pointer. It's a pointer that references memory that once belonged to you, but is no longer yours because you've deallocated it. And so what we need to do is, we can't lock the variable, because again, utopian society, variables are free for everybody, accessible, no locks. So what we can do is, we can just like erase any record of where we used to live. That way we don't accidentally go there, which basically means flush out of our brain our old address. In the case, because we are like Memento in the sense that we just remember what we have written down, then just like in the movie he does, he erases part of his memory so he never remembers them again, so he doesn't accidentally go there. So that's what we're going to do. We're going to erase the address that ATR holds, because that's our only way of knowing that 0x555 used to belong to us. How do we do that? Very easily. You just set it to something else. But in this case, the best thing you can do is set it to a variable that is known as null, but also null PTR will work, and even 0 will work. What these will do is they'll basically set it to 0. And then that's basically like erasing where the address used to be. And so now you can't accidentally go to your old place because you don't even remember it anymore. You've cleaned out all record of that. The second one, no PTR, also cleans it out, but it's a special one that they added in C++ 11. Another thing that you could sorry, getting ahead of myself here. Here's the one thing though. If you do this line of code, you're not 100% safe from errors. You're safe from accidentally going back to your old place. However, if I yet again try to do actually any of these lines, let me try copying these three. If I try to do this now, pretty much these two are going to crash my program. And then this one's just going to print out 0. So you're like, why? Like, why? I mean, at least before I wasn't crashing. I was just accessing things I shouldn't. But now I'm actually crashing. Isn't this worse? No. No, it's not worse. Because I would rather crash than access things that I shouldn't access. Plus, I have an easy way of checking to avoid this kind of problem. I can put an if statement saying if ATR is not equal to null, or not equal to 0, or not equal to null PTR, then do these lines of code. And then that is how I can check to make sure that this is a valid pointer. And checking for null is something very important. In fact, if I try to run this program on either of these, the error I would get is actually called a null pointer exception. I'm sure you've seen that if you've used computers long enough. Even if you don't program, you have seen that somewhere in an error message. Null pointer exception. So let me write that down actually. Have you all seen that? Has anybody seen that? Go ahead and put in chat. Yes, I've seen it. Oh, I don't know why. I accidentally put an extra equal sign. Thank you for catching that. Yes. Yay. So some of you have seen it before. That's great. That's great news. Okay. So if you play games or if you run about just any other program that's maybe not just like Firefox, then you probably have seen this elite ones. And maybe you Googled it. Maybe you didn't. You probably Googled it because that's probably why you remember it. But this is what it means. You're accessing a pointer that basically has null in it, which probably at some point had something else, but you know, it got deallocated and they got set to 0 to avoid dangling pointer problem. But something bad happening in their logic, and you ended up accessing it because bad logic, you know, bugs. So the way that you can kind of avoid this is you can say something like, if ATR is not equal to null, then don't run this. But you still got to deal with it with the else clause saying like, why are you accessing a null pointer in the first place, right? So anyways, this is how you solve a dangling pointer. So going back to the other problem was the memory leak, right? How do we solve the memory leak? The memory leak is solved with the delete. All you gotta do is add in your delete before you lose that address. So our solution is gonna be to call delete here of PTR. Now, we technically have a dangling pointer right here. Let me put some color here. Right here, we have a dangling pointer in theory, because if we try to access PTR at this point, we can still access that integer. However, it's not as much of a problem because immediately after the next line of code, we are setting it to something else, right? But if you're super paranoid, you know, you could put in between these two lines PTR equals null. And that would avoid the dangling pointer. But yet again, I would say that this is unnecessary. So when do you put it and when do you not put it? I would say, unless you're immediately reusing the variable, which is risky with its own, frankly, use a different variable name. You'll avoid a lot of errors by doing that. But if you want to use the same variable name, if you're immediately setting it to something else, that's okay. You don't need to put the equal to null part. But if you're not using it again, such as like, say, you know, you got something like int a, you know, gets new double, and then you know you can do basically like cin a and then cout a plus 1. In this case, a plus 1, this one actually will give you, you know, suppose that you read in 8, then this will actually give you 9 because you're not using the parentheses. So this will print out 9. Whereas if you did this, then it would print out the next address as value, which who knows what is in there. So This will print out 9. And then suppose you want to go ahead and delete it. So delete A. You don't put the dereference operator when you're deleting. You just put the variable name. And then, if you're not going to use it again for a while or forever, then go ahead and set it to null. Don't mix and match. If I'm used to using capital null, like NULL. They're all capitals actually. But if you want to use null PTR, all lowercase, then just use that one. Don't mix and match null PTR and null because they're a little bit different. Also, don't put 0. 0 is a bad one. Like, even though you can do it, and I did list it up here, it's not really good because it can confuse programmers to see A equals zeros, and they might think that's not a pointer variable, and it might confuse somebody, and confusions always lead to problems, so you want to avoid them. But yeah, so let's kind of summarize what we talked about before we start coding. So we talked about memory leaks. We talked about dangling pointers. These are both potential problems that dynamic variables come with, which is what we mainly talked about, which is dynamic variable allocation, or just dynamic memory in general, which is achieved by using new to allocate and delete to deallocate. We also talked about the ways that we use these things to solve this, right? So memory leaks are solved by using delete, and dangling pointers are solved by using null on variables that we just deleted, okay? I think that's pretty much all we talked about. I mean, we also kind of talked about hex addressing, which is how the addressing system works, and pointer arithmetics, which we will talk about later more. And for dynamic memory, we did both variables, individual variables, and arrays. 1D. But we will talk about multi-dimensional arrays pretty soon. Okay? So I think this went much better than yesterday's class. Look how much we covered in 1 hour. So, yeah. All right. So let's actually jump and start coding a couple of these things so you can see them again. Okay? So let's do that. By the way, are there any questions? Let's go ahead and create a memory leak, unless there's any questions, because you guys are very quiet today. That's kind of worrisome, actually. When people are quiet, it means that they're confused. But it's hard to read that when you're not looking at the person's face. You usually see the face of fear and death itself. So, anyways. Let's go ahead and create a pointer. So this is a pointer. And let's go ahead and create a normal variable. Let's put something in this variable. Oh, another thing. If you're not going to dynamically allocate a variable immediately after you create it, it's a good idea to set it to null at that point as well, just to avoid any potential risks. You said that using null you can cause a segfault. Can you explain how to avoid that? Yes. Yes. So let's go ahead and cause a segfault. See out PTR right now. And now we see it at its natural habitat, the segmentation fault and core dumps. It doesn't say null pointer exception because it's not cool, but yeah, if it was real programmer, would say that. So yes, you can see that how to create a segfault in 2 lines of code, because I don't really need this line. This is how. In fact, how to create a segfault in 1 line of code, I could probably achieve as well. Let's see if it lets us do that. Cout *0. I might need parentheses for this one. I think I need F permissive to run this one. Nah, it won't let me. So I guess how to create it in 1 line of, in 2 lines of code is the achievable method here, which is basically create a pointer, set it to null, and then see out that pointer. Do you see as to the why this causes a segmentation fault? Because we create a pointer and we set it to null, which means it's basically setting the actual value of the pointer is 0. How do we see that? Let's get rid of the asterisk. That is going to tell us what is actually stored in PTR, which is a pointer variable. So it should be an address, right? We see it's 0. Doesn't even have the 0x in front of it because it's just a 0, okay? So that means that we have a 0 stored inside of PTR. But PTR is an address. So address 0 doesn't really exist in our system. And if it does, we definitely can't use it. And so ultimately, how do we solve this problem? Well, this will sound bad, but basically you don't cause this problem in the first place. Is how you solve it. But that's not very helpful. But it's kind of like the sad truth. What you can do is you can add an if statement saying if PTR is not equal to null, then you hope that there's something valid in it. Otherwise, then you kind of just go with the concept of null pointer exception. Please fix me. I don't know, something like that. And now you just get the whole panic. But again, there's no solution because you shouldn't have a situation like this in the first place. It's more of like when you accidentally do it. And so you can add an if statement to check because it'll help you when you're debugging the program. But if somehow this reaches production code, then good luck to your people. So when a pointer is deallocated, then it cannot be printed. No, that's not true. That's not true. It's true that when you deallocate a pointer, you can still print it. That's called a dangling pointer. It's only that you can't print it anymore after you set it to null. So let's go ahead and do that. So I have a pointer. I set it to null because I want it to be safe. But next, I'm going to go ahead and actually make it point to bar. So PTR gets the address of bar. Now, I can go ahead and dereference that pointer. I can see the address. I can always see the address of a pointer. That it will not crash because it could be 0, it could be 1, but it's just a number in hex typically. Like that. So now we can see the address. I want to space it out, otherwise I'm triggered. So we can see that the address is somewhere in the stack. You can see it's a big number, pretty big, because FFF makes it really, really big. And so you can convert this probably somewhere around the 1 billion. And so that is where bar lives. And I can see out the value of bar by doing PTR. But you can see that I'm wrapping that inside a check to make sure that the pointer is not null. That's how you protect your code from accidentally. Because if you, for some reason, happen to forget to write this line of code, your program's not going to crash. It's just going to give you that message, right? Address 0, null pointer exception to fix me. So that if statement can help you, as long as you initialize your pointer to null, avoid segmentation faults. It's not going to fix the problem of you trying to access something that's null. It's just going to avoid you from hard crashing per se. You can more elegantly crash at this point, which is probably read some information, call some exceptions, and then close the program with a nicer message. So anyways, now let's move into actually dynamic allocation. So let's go ahead and allocate a pointer. So we're going to still use PTR, and we're going to do a new integer. That will create a brand new integer on the heap. It's going to give us an address that's going to be stored in PTR. So let's go ahead and actually see out that address to see it. So now we're going to call this the heap address. And this was technically the stack address. Okay? You can see that's a very small address because I guess the heap is at the bottom of the addressing system and the stacks are from the top. So it's kind of how it goes. Although technically if I add another variable in here, you'd see that it's going up. So that's because the addressing system here is different. But anyways, just assume that they're both going like this, as I said, okay? Even though the numbers are going to be different. Because they're counting, you can think of them both counting from their ends up this way. So it's counting up, but it's going down, okay? So anyways, we can see that the heap address, this is the dynamically allocated variable that we just made. And this one is the static variable where var lives. If we want to see where pointer lives, by the way, we can do that too. Because this is also a static, a stack variable. So that's actually where it lives. Because again, it has to live somewhere. As you can see, they're all very close. PTR lives here, and the var lives here. So this is vars. I'll put that so it makes it easier to see. And this is the dynamic variable heap address. So PTR's address is this. Var's address is this, courtesy of actually getting it from the pointer itself. And then this is the variable of the new integer that we just dynamically allocated. Okay? So let's go ahead and put something in that integer we just kindly made. Because right now, you know, it's printing out 0 here, but technically it could print just about anything. Because we allocated this integer and there was nothing in it. So let's store the number 42 in there. As you can see now, we can print out 42 with this. We can change this as many times as we want. We could do something like plus equals 1, which will add 1 to the 42. Semicolon. Oh, hello, dog. So, yes, we can add 1 to it, and we can do as much as we want. So now, if we don't do anything, if this is our entire program, technically, we have a memory leak because we don't deallocate the memory. Even though when the program ends, that memory is returned, and I would say that it's not quite necessary to return the memory because it's so close to the end, technically, it would be a good thing to return the memory that we're using. So, for example, after this line of code right here, we no longer use PTR. So even though, yes, the program ends and the memory would have been returned anyway, let's be the good neighbor and actually return it ourselves instead of the OS claiming it manually. So how do we do that? We use the delete. Delete PTR. Delete PTR would return the memory. We don't see anything happen when you run it, but internally that memory is now returned. However, PTR is now a dangling pointer at this point. Because if I was to try to do cout PTR down here, you can see that I can still access it. And it's printing out as 0, but this is lying to me because I can still access it, you know. But I guess this is a risk actually, because I might think that I still have a 43 in there, but in this specific case, in this specific system, it actually set it to 0. However, don't trust that's always the case. If I ran this on Sally or I ran this on the Mac, I might actually get a 43 out of this. Even worse, I can set this to 33 and then cout it again. And it still works. See that? I can still use that variable, but it's no longer mine, which means that I risk potentially crashing if that is given to somebody else. Now, the OS typically doesn't give out variables that it recently gave to you because it knows coders are dumb per se, and they know that they're going to make mistakes. So it doesn't just very quickly give it out. But if it was in a tight spot and it had no more memory left to give, then it probably would give it out. So it is still a very dangerous thing to do, and it is highly looked down upon for you to be doing this kind of thing where you're still using a variable you've deallocated. Okay? So for our purposes, there are tools that we can use to test programs to see if they have memory leaks, or if they have dangling pointers. They don't really have a tool for, but memory leaks they do. So let's go ahead and create a memory leak. How do we make a memory leak? Well, let's just make another pointer here. New int, right? If I do this, technically I have to delete PTR before I make another pointer. That would be no memory leaks right here. But let's add a memory leak by doing this, because now this and this is a memory leak. Yes, I agree with you. It should say 43, but delete in this specific system, for some reason, actually made it 0. Like it actually deleted it per se, but don't rely that that's always the case, because that's what's known as undefined behavior. If you run this in a different system, like if I run this on Sally or on my Mac or on Windows, it may not always set it to 0. It may leave it as 43. In fact, most of the time I'd say it leaves it as 43. I'm actually surprised that it put it as 0. So don't rely on the fact that it is putting it to 0. Either way, whether or not it set it to 0, it's still a dangling pointer, because that means that you have a pointer to somewhere in memory that doesn't belong to you. It doesn't matter what's there. but you still have access to it, which means you can write on it, which is bad because it doesn't belong to you anymore. So whether you get a 0 or a 43 is still is just as bad. Well, yes, testing SL is essential, but more than that, you shouldn't be doing dangling pointers in the first place. To avoid this issue, what you want to do is you want to set PTR to null. I guess just so you can see that you can use the other ones, I can do 0 as well. But of course, now I'm going to crash because I'm trying to access the dangling pointer. So I would have to wrap this in an if statement like this to avoid that. So I could put this all on the if statement. And so now I would see null pointer exception. Where's my else? Else without a previous if? Oh, I see why. Yeah, curly braces. Oh, I still crashed. Oh, yeah, because I never actually set it to null. So, oh, did I crash? Ah, ooh, I like that I crashed actually. Yeah, I like that I crashed there. See, that's bad that I crashed in this time. Look at that. This time around, I crashed. Even and why did this not stop the crash? Because when I deallocated PTR, there was still an address associated to it. But that address no longer belonged to us. So now this time around, I actually crashed. And I think it was because I added this PTR here. It kind of, it changed things. As you can see, even within the same system, now I'm getting undefined behavior. I want to see what's in here. Let's look at that address. Let's see what that address currently is. And let's just return 0 here so we can see it. This is the address. It's still the same address as before. I called delete. But this time around, I'm trying to access it. But it's still got a valid address. So this time it actually just crashed. Instead of giving us a 0 and allowing us to edit it, this time it didn't even let us mess with that. So interesting. Interesting that it switched, and all it did was because I added for some reason with the if statement, it decided to change its mind. So let's come out of the if statement for a second. I'm curious now. Oh no, I see why. It wasn't because of that. It's because I put the PTR 0 in here. That's why. So I set it to null. So I was trying to do null pointer exception there. That's why it crashed actually. There we go. Okay, so this time now we're back to the whole, it's a 0 here, but now we got 33 here. Okay, yeah. So now, if after I deleting, I want to solve the dangling pointer problem, I can say PTR gets null. I can use 0, or I can use capital case null or null PTR. Then I can see I get the null pointer exception, please fix me. But I don't at least access the dangling pointer. So take your poison. Pick your poison, basically. Okay? So let's talk about the memory leak, though. Here is a memory leak because I allocate a memory into an address, and then I can even print out that address if I would like right before I lose it. So you can see that it's going to be different. So we'll call it dynamic bar 1, dynamic bar 2. So we got bar 1 and bar 2. You can see that they're different. They're not necessarily next to each other. You can see they're actually pretty far away. They are 8 integers away, because that would be 32 bytes away. Bytes, not bits, but bytes. Okay, so there's stuff in between. We don't know what's there. It doesn't belong to us. It's part of the. It's in the heap. Probably another program did use that while we were allocating. Let's run it again and see if there's actually the same difference every time. Yeah, it seems to be always the same difference, but different locations in memory. So interesting. It's probably something related to our program that's being stored there. I do wonder what it is. I don't really do anything in between, so interesting. Interesting that that happens like that. But yeah, okay. Anyways, we have a memory leak, but we don't see anything happen. So what I'm going to show you now, and that's what I showed you at the end of last class, is a program to check for memory leaks, which is something that you will have to run to test your program before submitting them, because starting from the next assignment, you not including the Padme one, but that one I think, actually, I don't know if it includes that one. Whatever the PDF file says. If the PDF says that we check for memory leaks, we will. If it doesn't, then we don't. Okay, because the TA will read that and follow that. So if it's not in that case, then for sure the programs after that you will have to check. So you won't only just have to check whether it compiles and runs on Sally, but also whether there are any memory leaks or not on Sally. And so the program is called Battlegrind. It's installed on Sally. You can also install it on your local computer to test things. How do you install it? Just Google, basically, sudo apt-get Battlegrind, I guess, or in Mac, you have to use Homebrew. And so, yeah, so Battlegrind, A that out, you run it, and let's analyze what this program looks like. This program is going to basically print out the output that we have in the program. So you can see here the output still, all of the stuff the same. But around that, it's also going to print out some stuff. So up here is going to say who made it, you know, the version that you have. And then it's going to give you, after the program ends, so this is the output of the program itself. So this is the same stuff we would have gotten when we ran it. So you can see that it looks the same. We got 2, 4, 6, 7 lines. And here we got 2, 4, 6, 7 lines. They're a little bit different because the addresses are different. But ultimately, after the program ends, we get a little report. And this is the same report that the TA is going to be looking at. Let's look at what this report says. This report says that there was the usage of the heap when the program ended. It says that 72,000 bytes, so that's about 72 kilobytes, were used by the end of the program. 4 allocations were done, only 2 frees were made, and 73,000 bytes were allocated. That's not good, but at the same time, yes, this is to be expected. The worst part is looking at the leak summary. So the leak summary will tell you whether you have memory leaks or not. You have definitely lost, indirectly lost, possibly lost. These 3 lines of code should say 0 bytes and 0 blocks. If they say more than that, like they do here, you will lose points because that means you have a memory leak. The still reachable 72,000 bytes, you have no control over. That's actually your CIN and COUT IO stream variable that's having that. It's not a memory leak per se because, as you can see, it's under the still reachable. It just means that it wasn't. It's part of the implementation. It's not a bug. It's just how it is. Battlegrind thinks of this as something that's kind of bad, but it's not. You can Stack Overflow and explanation that they'll tell you that this is okay. So don't panic if you see this part, the 72,704 bytes in one block. That is normal. What's not normal is this. This is a memory leak. So how do we get more details? We could run this rerun thing, and I think it might help, but not really. So Battlegrind is not going to be your cure, where it's not going to tell you exactly what's wrong. It's just going to tell you that something is wrong, and then it's up to you to figure it out. So I run it again with leak check full, and as you can see, it still didn't really give me anything. It will sometimes give you errors here, which kind of give you hints. I do expect there to be 0 errors from 0 context, okay? If there isn't, that means that you're going to lose points as well. So let's go ahead and delete this, since that's going to be the solution to our memory leak, and rerun Battlegrind. First, you got to recompile the program, run Battlegrind again. Now you can see that things change. We have no leaks. See, 0 bytes and 0 blocks. All these this still says the 72,704 bytes in one block. It'll always say that. The 4 allocates and 4 free. That is probably we delete and we delete. Probably because the way we're using the program. Why do we say 4 allocates and 4 free? We have delete and we have delete here. So yeah, don't worry about that if those are not matching. Probably I might have something in here. I don't think so. But what you definitely want to make sure is that these all say 0 and that these say 0 errors. That means that your program is memory leak free for the most part. There could be things that this thing sort of doesn't you know, it slips through. But if this doesn't check it, then you won't lose points for it. This, of course, works for like relatively small programs. In the real world, there is not really a way that you can run like an entire, like Call of Duty, like the entire game. You can't just run it to Battlegrind, because this is actually a really slow process. Like, you will see a major slowdown when you're running this program. Like, if your program takes 1 minute to run, with Battlegrind it's going to take like 5 minutes to run. So it gets a major slowdown because it's monitoring all these addresses, and it's sort of like middle ground between you and the OS, so that it can keep track of what you're missing. So you know, it's not ideal in the real world. There are some memory leak testing tools available, but this kind of gives you an idea of that. Plus, more than the real reason why you're doing this is because we're trying to teach you good programming practice to avoid memory leaks in programs where you have control of that, such as toy programs like the ones you do in school. So I suppose I can try to show you what a memory leak ridden program might look like. I can probably find one. Let me see. Let me just try opening one of my other programs, like Battle Royale or something. Let's see. Dropbox, blah, blah, blah. By the way, any questions, go ahead and write them out now. Let's try the CSGO program. That probably has memory leaks. Assignment 12. I haven't run it. I actually forgot the arguments to run this program. Okay, that one doesn't compile. Let's try this one. I was messing around with that program, so I probably broke it. Oh, I know what it is, actually. No, it's the, I forgot the flag. Ooh. Ah, I need the end curses library. What's the library for end curses? I forgot. Curses? I forgot what the library is for the ln curses. Hold on. Compile with end curses. ln curses, there we go. There we go. And I gotta go to map file. Okay. CSGO. Mirage. Okay, so now let's make this. See if can you even see this? Yeah, you can. This will look bad because it's gonna be big. But let's just see if it works still. Okay, it works. Cool. Okay, cool. So now let's run Battlegrind on this. So when you want to run Battlegrind with command line arguments, you just put them right after. So like this. Actually, I think I can probably run this on the test map because it's much smaller. So test map CSBO. Text. Okay, now we're running it in Battlegrind. So okay, oh, AI is dead. Oh no, AI worked and killed me. Okay, cool. So human dead. Now let's just run the program and it finishes. So let's see our memory leaks here. So we got in use at exit 145,000 bytes in 388 blocks, 647 allocs, 259 frees, 173 bytes allocated. Leak summary: 39 blocks, we lost about 2 kilobytes. Indirectly lost, we lost about 1 kilobyte and 17 blocks. Possibly lost none. Still reachable is pretty high too. And 155 errors from 2 contexts, but we don't. It didn't show them. I want to see the errors. It's I think there's a command to show the errors. Let's do rerun with -b. Let's try -b. Oh, it didn't. Well, this time it ran, but it gave me a message saying invalid map file, so that's what it was. So I think I gotta give the argument before that. That should be. Okay, so I already had errors before the thing even started. And then let's just. Okay, so here we can see some nasty error messages. Conditional jump or move depends on initialized value. That means that I jumped something. I made a movement on something that was not initialized, or at least it thinks that I did. But I probably don't have errors. I never code errors. My code must be perfect. So yeah, you get a lot of verbose things here to try to help you out. As you can see, everything is bad because it's putting question marks like, huh? But yeah, so this is what Battlegrind would look like when you're actually running it on something more serious. So this is actually a 302 assignment that you're looking at here. That was your final project. We'll probably reuse most of that for the fall for 302. They made a CSGO 2D game. So yeah, it's pretty fun. Pretty cool assignment, actually. I'm quite proud of making that. It's a very creative semester. All the assignments were brand new that semester. And fun times. So now that I made them brand new, I feel like I should reuse them because they're pretty cool. So yeah, anyways, let me switch over back to this. So I can see that you guys are looking at the same. It is pretty cool. The PDF explaining it is like 30 pages long though. Because yeah, it escalated pretty quickly. If you're curious, this is what it looked like. So that's it, easy. So yep. Jokes and stuff. So anyways, yeah. Talk about some of the games, the random stuff. But anyways, you know, we could actually, you know, in theory, in 202, you could make part of this. Not the AI, but you could make like a top thing, you know. So I could actually do as your final project, part of it, not the entire thing, and then you could finish it when you get to 302, you know. So I'm still debating on that. I think I'm gonna stick with Battle Royale, but I don't know yet. It's summer, so it can be pretty crazy to do this during summer. You know, it took them about 2 weeks. It is actually like Battle Royale, you know, on steroids or whatever that you want to call it. So because it's a lot of top-down movement. So I think we'll see. But anyways, coming back to memory allocation and stuff. The whole purpose of me showing you that is so you can kind of get a feel for how Battlegrind would look when you actually have errors in your code. And unfortunately, you will have to fix those errors or lose some points. You know, you have to decide if it's worth your time going through and deleting stuff. So my tips for avoiding problems like this. Tip 1, if you allocate a variable, even if you haven't written the code, at the end of your code somewhere, deallocate the same variable already. So if you're writing a program, you know, and at some point in the top of the program, you're going to say something like int ptr, or what is a different variable name, in t gets new integer, immediately at this point in time in your life, go to the bottom of your program, at least for now, or the bottom of your function if you're doing this in a function, and do delete t. Just so you know that you're supposed to do that, okay? You might move that somewhere else before that, but that way you kind of remember, you know, you're like it's a little reminder you have to delete that at some point. Furthermore, you typically want to count the number of times you do new, and you want to have an equivalent number of deletes. Things get complicated because you might have a delete in a for loop, and which scenario it's you know, it's harder to keep track of how many deletes you have. So when you're running Battlegrind and it says the number of deallocs and you have the number of allocs, that can kind of give you a hint if you have problems where you're not deleting enough. But that's probably going to be your memory leaks 99% of the time. Now, Battlegrind does not check for dangling pointers. It might say with the still reachable, that might be kind of checking that, but that's not the bigger problem. Dangling pointers are only bad if you actually dangle with them, I suppose, like you're able to access them. Memory leaks are bad always, so that's the ones you really want to avoid. So let's just make, for the last 10 minutes, another program here and give you one more example that we haven't gone through yet. And that's going to be dealing with arrays, because we haven't actually made an array yet here. Oh, it still says assignment 12. Buckets. Hey, there's our bucket. Let's close that as well. Just open the new terminal here. G++. Let's just make sure that this still compiles, so when I give it to you, it's okay. So there we go. All right, cool. Let's go ahead and close these out. So I still want to show you next time, so that was going to be tomorrow, how to allocate things using the C style, so malloc and alloc and free. We'll do that tomorrow, and then we will do more array stuff tomorrow. But for now, let me just show you how to do a one-dimensional array in with dynamic memory allocation. Okay, so let's do that. My dog came and left. Okay, so let's go ahead and create a dynamically allocated array that the user is going to read in. And we're going to go hardcore into the dynamic stuff. So we're going to make a pointer called count. That's going to be an integer. Now, this doesn't really have to be dynamic, but we're going to make it dynamic because we can. And then we're going to read into that count from the user. Let's go ahead and see out a message saying enter. Actually, let's make the message into a string pointer too. Gets enter size of array you want to make. Yeah, good point. That's where I'm going to put that. Actually, not there. Cout message end line. There we go. Cin count, and then that's just going to read in the value, and then we're going to allocate the array on that size. So we're going to call it int array gets new int, and then the size, which is going to be given in count. And then from there, we are going to just throw random stuff in there. So for I equals 0, I is less than count, I plus plus. We're just going to put in that spot, I, you know, whatever. And then after that, we're going to go ahead and print it out. So int I in AR. Actually, I want to see if this one will work with the pointer. I'm not sure it will, so be a good test to see if it works. Okay, so yep. And of course, we're gonna put the how to solve the memory leak problem, but I'm gonna comment it out so you can see the memory leak. So we need to delete a couple of things. We need to delete message. We need to delete count, and we need to delete the array. How do you delete an array? So you actually put the square brackets in front like that. This is weird. This is weird. Don't feel bad. It's just weird. You have to adapt to it. You have to accept that this is how you put the delete for an array. You put the square brackets in front of the variable name. So just embrace that. I opened this by accident. There we go. Let me minimize this. Okay. So this is called mem2. Let's see if we missed any semicolons or random things. It definitely didn't like the AR thing. Oh shoot, we never allocated this. So that's a problem. New string. And then error, expected we're missing a semicolon. Line 9 here. All right, so the warning is giving us is just because we don't have the std11. Which, yeah, so it doesn't like the fact that I'm using, so I'm actually curious what would have happened if I ran it using this method. Would it have just crashed? Or what would have happened? Yeah, bad things happen. Okay, so that's because the range for loop doesn't really work because this is a pointer. So that's okay. We'll just use the old school for loop. I just wanted to test if it would work with that. That would work with a vector and things like that because they have a size, or an old school array because it has a size. But that one doesn't have a size, so we could force it to get working, but I don't really want to go into that right now. So for now, we're just going to do cout R1 and line. In fact, you know, I don't like having two for loops. We'll just do it like that as we go. Okay, so let me go ahead and comment out the deletes just so you can see the memory leak. And let's go ahead and run this. Okay, so how big do you guys want to make the array? Any suggestions on how big you want it, you know? Otherwise, I'm going to put a 8. So going once, going twice. Maybe there's a big delay on the chat. So, oh my gosh, I know you're going to go with a big number. The problem is it's going to spam tons of numbers here. Well, it did. It made it. Now we made it all the way, you know. So there you go. So now I can't scroll up to the top though, so that's great. But you know, if we did a smaller number, just so you can see for a second here, you can see at the top it says enter the size and whatever, and then it puts the count. So let's go back to our really big number of, you said 100,000. So there's 100,000 size array. I'm actually surprised that it didn't complain about that. It's probably because it's an integer array. So now let's go ahead and do Battlegrind. So that's going to be fun for Battlegrind. And so it's going to ask us to enter the size. So we're going to go, there we go. And then it's going to be a little slower. As you saw, it was a little bit slower if you watched the replay of both of them. And let's see what we got here. So we got 7 allocations, 2 frees, in use 472,000. So we lost about 400 kilobytes in 3 blocks. And indirectly lost, that was probably the message, if I was to guess. And then the still reachable, again, that's your scene and see how this was going to be there. So yeah, we got a pretty decent memory leak. Let's go bigger. Let's go to 1 million now. I think that's 1 million, right? Actually, let's not go to 1 million because that's going to take a while. Okay, no, that'll finish. Like we give it about a minute. Class time is limited though. But while that runs, let's go ahead and fix our memory leak so that we can run it one more time. And then it's almost done. We're almost there. 6, 7, 8, 9. Cool. This time, our memory leak is in the megabyte range. It's about 4 megabytes. Does that math actually add up? Well, think about it. Each byte, each integer is 4 bytes, right? And you got about 1 million of them. So 4 million bytes sounds about right. The 36 here is probably coming from the integers 4 more. So that's 4. And then the other 32 is probably coming from the string, if I was to guess. The string is probably around there, or it could be from here. I'm not 100% sure on. Yeah, we got count, we got message, but at least the 4 million sounds about right because again, each integer is 4 bytes. 1 million bytes is 4 times 1 million. That's 4 million. So that's kind of about what we would expect to see there. So we go ahead and we, you know, let's have 1 memory leak left. Let's just have the count left. But let's go ahead and delete the big one. So this time we're not going to run it for that big. Let's do the 100,000 only. Keep putting those by accident. This time around, oh, I forgot to compile. So I was like, fail. Try that one more time. This time we only have 4 bytes lost. And that is definitely coming from the count. So we fixed it. So yay. As you can see, memory leaks can be pretty big and scary when it's just 1 line of code that's missing. If you just forgot that delete brackets AR, you get a really big memory leak. Well, relatively big. 4 megabytes is not that bad. I mean, we have gigabytes of RAM. 4 megabytes isn't going to kill anybody. But for the purposes of this class, you would lose points. But as you can see, you know, 1 line of code can create a ton of memory being lost, if it's especially something like an array. But now that we have our 3 deletes, we have everything nice and clean. So, you know, it feels good kind of thing, right? So, of course, if we want to be extra safe, we can also set the pointers to null. Let's use null PTR this time. We haven't used that today. So count equals null PTR. And then AR equals null PTR. Of course, it's at the end of the program. I don't see a purpose of doing this. But if there was more code beneath here then it will definitely be worth it, just to avoid accidentally referring to memory that we shouldn't. Gotta put the flag std equals C++11 because no PTR is a C++11 thing. One more. And so you can see it's still the same, but in this case, we don't have dangling pointers. So that's a nice thing to know. So really, everything is the same. You don't see Battlegrind a difference, but dangling pointers, you know, it's a good thing to get rid of them. So any questions? I know some of about maybe half the class was hopefully reviewed from yesterday, but I really wanted to recover it because pointers is one of the hardest topics in the class, and I didn't feel like I did justice yesterday with how I was feeling. So we have the time, so it was worth spending it on today. So are we on video 6 or is this video 7? I don't think I updated that. No, that was video 6. Oh, cool. So any questions? Got anything? Going once, going twice? So like I said, tomorrow we'll pick up from here and we will talk about more array allocation. So I showed you just how to do a basic 1D array, but I'll show you how to do multi-dimensional arrays, and I'll also show you malloc and free, which is the old school C way. So we have a question. So if we put more code below, then we use null and then set the pointer to new values. No, you set null so you don't accidentally access it. But if you ever want to use the pointer again for anything else, then you can go ahead and set it to point to something valid, such as a new allocation with new, or pointing it to something that you currently have right now, like aliasing a variable, and so on. But I'm just saying, whether or not you touch that variable again, if that code is not at the end of your entire code, it's a good idea to set it to null so you don't accidentally access it. So you don't have to reuse the variable. In fact, I would recommend you don't reuse it so you don't accidentally get confused. Use new variables. We have lots of memory. There's no point in trying to go that cheap with memory. So when we set a variable to null, then we cannot use it again at all. No, you can. All you're doing is, remember, a pointer variable is just storing an address. You're setting that address to be 0. That's all you're doing. And the reason you're doing that is so you don't accidentally access that address, which used to be yours, but is no longer yours. And by putting it at 0, if you try to access address 0, you're going to crash. So you're doing that just to erase the address per se. Okay? You're resetting the address. It's like, imagine you read a number from a user and then you want to erase that number. There's no erase function in C++. You can overwrite a number. So you can overwrite it with something like a 0 just to kind of get rid of it. That's what you're doing when you're setting it to null. But you can reuse the variable as much as you want because it's still just a variable. If I have an integer a in my program, I could use it for like 20 different uses, As long as I go one at a time, I can do that. As long as they're all usages of integers, I can do that. So same with the pointer variable. If it's an integer pointer variable, I can use it to point to any integer at any time. What I'm saying is that if at some point it was pointing somewhere that was dynamically allocated, and now you deallocated that point in memory, you want to make sure it's no longer pointing there because that memory is no longer yours. And one way to do that is, again, there's no erase function. So the second best thing is just to set it to 0, which is what null does, just so that we don't accidentally access memory that's no longer ours. At that point, we can never use this variable again, or we can use it again, but it's up to you. I'm just saying it's not a good idea to reuse it because you can just create a new variable and it can open itself to errors if you keep reusing the same variables. Like there's a higher chance if you thinking you have access to something that you don't have access to, and that kind of thing. So, yes. That's a long answer to your question. The green screen is messing with my eyes. I gotta fix that. It used to be fixed, but I guess it got messed up again. Cool. All right then. So, thanks for watching, guys. I shall see you tomorrow. If you have more questions, go ahead and post them on Discord. I will go ahead and set up that next assignment, which is going to be to redo assignment 1, but using dynamic allocation. But to be able to do that, we still got to cover more about arrays because that's what you're going to do. So that we shall continue the topic tomorrow. So you can also ask questions tomorrow as well at the beginning of class. So have a good rest of your day, and I shall see you in 22 hours from now. Bye, everybody.